Welcome to this video called Embedded Hardware, which is taught as part of the SoPC course. So before going directly into details, we are going to look at the definition of an embedded system. If you look in the literature or browse the internet for a while, you'll find a lot of definition of an embedded system. One definition among others is that an embedded system is nothing more and no less than a particular circuit that is lodged within a larger hardware device. Another definition is that an embedded system is a standalone system designed to perform a specific task. The properties of this type of systems are that they generally feature a computing unit. We're talking about embedded processors, which are usually simple and are to be distinguished from conventional so-called general purpose processors like the ones you have in your PCs and laptops. Another of its properties is that this type of system usually has a relatively basic user interface. That is to say that it does not have complex elements such as a large screen, a mouse, a very large keyboard, but simply very basic input-outputs such as buttons, switches, LEDs to ensure communication with the outside world. Regarding the constraints on this type of system, we can say that these are usually real-time compatible because of their application domain, which has time execution constraints. On the other hand, they are often small due to the fact that they are part of a bigger device. Finally, these systems are generally autonomous, which means that they have their own power source, which constitutes an additional constraints on their power consumption. Some examples of this system are cell phones, smart digital watches, for example, medical imaging systems, but we can find other examples of embedded systems such as devices that will manage the spin drying in a washing machine, a GPS, control systems in cars or planes, etc., etc. You can see that there are a multitude of such systems which correspond to the definition. Embedded systems can usually contain more than one component. The first of these is the processor, which will provide the computing power and allow processing to be carried out. Associated with this processor, there is always a memory, which will be used to store the program which will run on the processor. And there, we find different types of memory, such as memories which are non-volatile, generally those which contain the program or code memory. These are, for example, flash-type memories, which are the basis of devices such as USB keys or SD cards that you all know very well. The other type of memory is said to be volatile, meaning that the content can be erased if the power is off. This is particularly the case with RAM memory. In addition, there are a number of peripherals which can be associated with the processor, and these peripherals are used in particular for communication between the processor and the outside world. Some of these devices can also be used to debug the system or to provide timing information that will help synchronizing the flow of operation. This is particularly the case with timers. In this course, we will focus on different types of embedded processors. The first family is based on what are called microcontrollers. And it's this type of processor that commonly dominates the embedded industry today. The second type of family is based on circuit called ASICs for application-specific integrated circuits. These are circuits which, as their name suggests, are specific or dedicated to a particular application and are optimized for that application. The last family is based on FPGA type circuits that you have already met in previous courses. These are reconfigurable circuits, which were previously used for prototyping, but that have become more and more used in commercial circuits due to their high level of performance and flexibility. If we are interested in the flexibility of this type of processor, the figure below shows that the ASIC are the circuits which have the least flexibility, but which have the most performance. Microcontrollers, which can execute several types of applications, are more flexible, but with less performance than an ASIC circuit. Finally, the FPGA are very flexible since they can be reconfigured even during runtime, but will also have the least performance because the clock rates are usually low compared to their counterparts. So let's start by studying processors based on microcontrollers. As I mentioned a little bit earlier, most of the processors in the world of embedded systems are based on this type of microcontrollers. They are often compatible with most of the applications that we find in real life. A single microcontroller usually has internal memory, which is used to store the code that is executed by the processor, as well as data that are used during computation. Additional peripherals may be found, like timers, for example, floating units, floating point units, memory manager, interrupt managers, etc., etc. Today, most of microcontrollers are usually programmed using the C language or even C++, which are high-level languages. They can also be programmed in assembly, but in more rare cases. The figure on the right here shows the evolution on the number of microcontrollers in the specific field of the Internet of Things over a period ranging from 2012 to 2022. These projections are made in different fields, such as industrial automation in blue, smart houses in red, consumer electronics in green, and then other cases are given in purple. We can see here the rapid increase in the number of microcontrollers in the field of IoT. It has an exponential trend, actually. The second family consists of processors based on ASICs. Remember, ASIC stands for Application-Specific Integrated Circuit. There are different ASIC types, namely the full custom, the standard cells, and the gate arrays that I'm going to describe now in detail. The first family is the full custom technology. In this type of circuits, the design is performed at transistor level. That is to say that designers have access to the transistor architecture itself. They can directly design the transistor and the connections between them using what we call masks. The advantage of this type of circuit is due to the fact that the design at the physical level makes it possible to optimize the density of the transistors. Designers can also size the transistor channel according to their requirements. This can lead to very high performance. We talk about several gigahertz in terms of clock frequency that drive the entire device. The major drawback of these circuits is that they are very difficult to design and build, and that they require several years of design, validation, and test. For a single chip, the costs that are generated by the design are often prohibitive and are reserved only for large industries which plan to produce this type of circuit in mass in order to reduce the development cost. An alternative to full custom circuits are these standard cell circuits, or standard cell ASICs. These ASICs are made up of basic cells that have already been designed and prefabricated and that are available in a library. These components consist of a group of transistors as well as interconnect, allowing these transistors to communicate with each other. These circuits are usually used for volumes ranging from 10K to 1 million pieces a year. They present much lower development costs, but also have lower performance since the transistors cannot be tailored and optimized as in the case of full custom. Regarding the operating frequencies, they can go up to several hundred megahertz, but cannot go very high. Sometimes 1 gigahertz, but not that much. The figure here shows the total development cost for standard cell circuits according to the technology, and in particular, according to the size of the transistors from 0.18 micrometers to 45 nanometer. We can clearly see on this graph that development costs increase significantly on all the specs, namely the mask design, software, as well as test and verification. The smaller is the technology, the bigger the costs are. The last type of circuit is the gate array. These circuits are based on basic cells, which consist of a collection of transistors or logic cells. These cells are usually arranged in rows or columns, that is to say in a matrix, in fact, of elements that are previously placed in the silicon. Designers just have to create the layers of connection between the different components and configure the logic cells to perform a given function. This figure shows here an example of this type of circuit, somewhat dated, but which clearly shows the philosophy behind this type of circuit. We can clearly see the different components arranged in rows and columns with the layers of metallization here in black, which ensure communication between the different cells. An example of such circuits are the FPGA, which are the field programmable gate array. They are composed of a programmable matrix of logic cells with a network of interconnections that is also configurable. We also find particular cells dedicated to IOs, input-outputs, which are also configurable. Today, FPGAs have become very complex circuits which can implement intensive computing functions. One speaks of hardware accelerators. These accelerators may execute complex signal processing algorithms, such as complex transforms implemented in DSP blocks. We may also find a large amount of embedded memory, hardware multipliers, and even processors. The advantages of this type of circuits are their high flexibility and low cost. The current figure shows the organization of an FPGA. In particular, we see a matrix of logic elements arranged in rows and columns. Each logic element is able to implement a particular logic function, and it communicates with the other logic elements via programmable connections. If we take a look at the overall architecture of a logical element, we can see that it's made of a lookup table, LUT, which is the equivalent of a small memory with 4 or even more inputs. This memory can only store 1 bit per address. A memory with 4 inputs can therefore store 2 to the power of 4, which equals 16 1-bit word. Associated with this lookup table, there's a programmable D flip-flop driven by an external clock. A programmable multiplexer makes it possible to select between the output of the lookup table or the output of the flip-flop. In a logic cell, it is therefore possible to implement not only combinational circuits, but also sequential ones. The example here shows the implementation of a particular logic function and the corresponding content of the lookup table. Here we have a 4-entry lookup table with A, B, C, D as inputs. The lookup table therefore has 16 memory cells to store just a single bit. In the current configuration, we see that only 3 bits have been set to 1. This one, and this one. So if we look at the combination in the corresponding truth table, the bits set to 1 correspond to the term, to this one, D bar, C bar, B bar, A, and D bar, C bar, B, A, and D, C bar, B, A bar. The logic function which is implemented in the lookup table is therefore this one. S is equal to this term, or this term, or this term. In summary, we can say that a 4-input lookup table can store any 4-variable logic function. On the other end, the logic cell will only have one output. So current FPGAs have up to 7 inputs lookup tables. That is to say that they can implement much more complex functions of up to 7 variables. The size of the memories is therefore much larger, since it has 2 to the power of 7, that is to say it's 128 1-bit memory slots. But the principles remain the same. That's what is very important. The figure now you see here shows that it's also possible to configure the interconnections between the different logic cells, in addition to the contents of the cells themselves. These interconnections are used to make different logic cells communicate with each other so as to perform much more complex logic functions. The step of implementing the connections between these cells is called routing. We will come back to this concept later when we are going to describe the design methodology. The interconnect is made by metal tracks. These tracks are also arranged in rows and columns, as you may see here. At the intersection of a row and column, there's a transistor, which can also be programmed. So basically, if the transistor is considered to be on, a connection is made. If it's blocked, the connection is not made. In SRAM type FPGAs, it's the content of the transistors between the row and the column that establishes the connection. Switching off the power erases the content of all transistors and therefore the interconnections between the cells. So the fact of switching the power off also erases the contents of the various logic cells. In this case, everything happens as if the circuits were blank. The figure you see here shows the building blocks of an FPGA. It shows the logical cells arranged in matrix, here in red, all the square here in red. There's also arranged in columns embedded memories, in purple here, which are generally available in the form of large blocks, which are pre-mapped in silicon, and which allows to implement a larger amount of memory in addition to small logic cells. There are also specific DSP blocks, here in blue, that make it possible to execute complex signal processing functions. These blocks are often built on multipliers and perform operations such as filtering or transforms like FFT, for example, which are very, very demanding in terms of logic resources. Around the circuit, there's a certain number of elements which are in green here and which are input-output blocks and which will allow the FPGA to communicate with the outside world. These input-output blocks or cells are special and have an architecture that is a little bit different from logic cells, the red ones that are arranged in matrix. So this new figure here shows an example of a DSP block available in the Intel circuits of the Straight X5 family. We can see that these blocks work on quantities of 72 bits, have two multipliers, 18 by 18, as well as an accumulator here and an output register. These DSP blocks are also present in silicon from the manufacturer of the circuit and may or may not used by the designers. So note that the DSP blocks present in the Xilinx families are quite similar to to those which are presented here. Okay, now the slide shows here the main families of the FPGA devices and the different vendors. The first one is the Xilinx family. One of the most famous families of FPGAs are the Vertex ones. These are high-performance SRAM-based FPGAs dedicated to complex applications requiring a lot of computing power and resources. The Spartan family consists of devices with a smaller size and are reduced versions of Vertex. The Cool Runner family is a family of specific devices that are called Complex Programmable Logic Devices, or CPLDs, with an internal structure which is quite different from FPGA and that is much more simple. In Intel, or Altera, we find nearly the same technology. The Stratix family consists of high-performance SRAM-based FPGAs nearly the same as the Vertex and Xilinx. The Cyclone family are low-cost devices that are used for cost-critical applications and are similar to the Spartan family in Xilinx. The other vendors are often based on different technology. For example, MacroCMI uses the anti-fuse technology, which is a radiation tolerant and that is focusing on specific parts of the market, space applications, avionics, etc. These applications have specific constraints that cannot be met by SRAM devices. The anti-fuse technology is not like the SRAM, meaning that switching the power off does not erase the memory contents nor the interconnect. It relies on the flash technology, which is similar to the technology that you have in your USB keys or SD cards. In this table, I'll summarize the different features of several circuits of the Xilinx family, namely the Kintex UltraScale and UltraScale Plus, the Vertex UltraScale and UltraScale Plus, and the Zinc family, which contains several processor cores. We'll come back to this point in the other parts of the course. In this table, the number of logic cells for the largest Vertex UltraScale FPGA circuit goes up to almost 9 million system logic cells. We also find the amount of memory available in the block memories. The number of DSP blocks here is also mentioned. We can see here that it can go for the largest FPGA up to 2,288, which is huge. The performance in terms of giga-multiplication accumulation per second reaches more than 20,000 for the Vertex UltraScale Plus. These circuits also feature a high number of transceivers, which corresponds to very high-speed input-outputs that can reach 8,000 gigabits per second. This table also includes the number of input-output pins, which can be as many as 2,000 for the largest FPGAs. So it seems obvious that today's FPGAs are huge components with a huge amount of resources and that they are capable of performing very complex operations and implementing a wide variety of applications. Their role today goes far beyond the simple circuit for prototyping. This small figure shows the architecture of the logic cells of a relatively old FPGA since it's more than 20 years old now. The circuit is a Vertex FPGA from Xilinx. So we can see on this small logic cell that it has a memory that can be configured as a lookup table, a RAM, or even ROM, read-only memory. We can also see that it has 4 inputs, A1, A2, A3, A4. There's also a flip-flop here with its input D, its output Q, and additional control inputs such as CL, CE, clock enable, or reset inputs, synchronous or not. What we see in the middle here are multiplexers or logic gates that actually ensures the data path through the logic cells. In fact, what is important to note is that the architecture of such a logic cell has not really changed that much since 2000. What has changed actually is the density of cells within a circuit and eventually the complexity of the lookup table, which now has 6 inputs for most of them. Of course, technological improvements have taken place, but these improvements concern more the integration density of the hardware resources than the nature of the architecture itself. On this new figure, we see the architecture of a logic element of the competitor's company, which has now become Intel. Basically, we see that the architecture is relatively similar to a logic cell architecture from Xilinx. We find the lookup table here with the 4 inputs, as well as the flip-flop, and a logic circuit made up logic gates and multiplexers, again, to ensure the data path inside the cell. The figure here shows the overall architecture of this Stratex FPGA circuit from Intel. It clearly shows the matrix structure of the logic cells that are grouped in a logic array blocks or labs at Intel. We can also see that they are arranged in columns. We can note that there are columns of M512 RAM blocks that are small blocks of memory containing 512 bit. Larger memory of 4K bit in green on the figure, also available on the device here. The 2 yellow blocks represent mega RAM blocks, which are blocks with larger quantities of memory. Finally, we see the DSP blocks that are also arranged in columns in this type of device. Finally, on this slide, we have a certain number of elements that constitute an FPGA of the last family of Xilinx. In this type of circuit, we can find today application processors that are Cortex A53 ARM processor with 4 cores, quad cores. These cores have virtualization capability, and we'll come back on this point later in the course. There's also possibility to have specific real-time processors with the Cortex R5 type from ARM again. Other specific processors such as graphics processors are also included inside the FPGA. And next to the processor, we find a logic area which finally contains the matrix of logic cells as described previously. This makes it possible for designers to implement hardware accelerators to enhance the processor's performance. Well, that's it for this course. Next time we will talk about embedded processors and we will give some example of the most popular ones. So thank you for watching and see you soon.